let's define r sub 2 of an integer n to be the number of integers ab such that a squared plus b squared equals n. So, I mean, in other words, r2 of n is the number of ways to represent n as a sum of two squares. And studying this function is somewhat classical, interesting for a couple different reasons. There's some famous results about when this is zero, but today I want to talk about asymptotic results for this. So the average behavior, the statistical behavior of this function. So in Hardy and Wright, section 16.10, there is this result that R2 of n is equal 4 times sum of the divisors of n of, and then here is going to be minus 1 d. So this here is the Kronecker symbol. And it is a Dirichlet character. So the value of this explicitly is minus 1d is 0 when d is even, and minus 1 to the d minus 1 over 2 when n, or when d is odd. Okay. And what this means is that, well, so we can recognize this, say, as a Dirichlet convolution, and so this implies that if we look at the Dirichlet series, some n from 1 to infinity of R2 n over n to the s, this is equal to 4 times the sum n from 1 to infinity of 1 over n to the s times the sum m from 1 to infinity of minus 1 m to the s. And this is, of course, the Riemann zeta function, and this is going to be a Dirichlet L function. And this comes from just recognizing this as being a Dirichlet convolution of 1 and this Dirichlet character. And this Dirichlet L function, written explicitly, is 1 to the minus s, and then minus 3 to the minus s, plus 5 to the minus s, minus dot dot. Okay. And because we have this representation as a product of meromorphic functions that we understand the properties of, this implies, once you do the whole Perron's formula business, that the sum n less than x of R2n And here I'm not going to write an error term, I'm just going to write it's asymptotically. And this Dirichlet L function isn't going to have a pole at 1. So the rightmost pole is going to come from the zeta function. So it's going to be 4 times 1, which is the residue of the zeta function. And then here we're going to have L1 of this Dirichlet L function. And there's this question, what is this, right? So here's some ways you can do this. I'll give you 3 ways to figure out what this is. So way number 1 is look it up. So I mean, maybe this is a bad way to put it. Really, what I should say is ask a computer. So you can do this in your own browser using, for example, Wolfram Alpha. And let me just show you what that looks like. So you can go to Wolfram Alpha and you can ask, and it looks like this. So the answer is pi over 4. And now, okay, to know exactly what to type in, well, how do you know for sure that you have the right Dirichlet character? I checked it this way. All right, so now you're sure that you have the right Dirichlet character. Okay, so it's pi over 4. Cool. What is way number 2? So way number 2 is that there's this formula from Leibniz. Oops. And okay, I don't see a specific date, but there's a lot of history on the Wikipedia article. So the Leibniz formula for pi, and you can look this up on Wikipedia to get the history, which I think is worthwhile. And this formula, which is, I think, quite well known, is that this alternating sum of the reciprocals of the odd integers, positive odd integers, is pi over 4. And you can see that this is exactly this Dirichlet L function when s is 1. So that also tells you that the value here is pi over 4. Now, the third way is, I think, the most interesting way. So the third way is using what's called the class number formula. And I can't talk too much about this because I don't want to talk about algebraic number theory. But so I can give as references these notes from Kimball-Martin. He has some modular forms notes, and then there in section what's currently 7.1.2, he gives, let me check exactly what the form is, that if you take k, this is an uppercase K, to be the quadratic field Q adjoin square root D. And if you don't know algebraic number theory and don't want to think about it, you don't have to worry about any of this. And then we'll say delta is the discriminant of k, which here is going to be d if d is 1 mod 4, and it's going to be 4d if d is 2 or 3 mod 4. Okay, and now you can define this character chi of n to be this Kronecker symbol discriminant over n, and then the Dirichlet L function L1 chi, so this is going to be in the case where d is negative, so you have an imaginary quadratic field, and then the value at 1 of this Dirichlet L function is 2 pi times, and then here this can be h sub k, this is the class number, divided by, and then here there's some w, and the absolute value of the discriminant, and here w is 6 if d is minus 3, 4 if d is minus 1, and 2 otherwise. Okay, and from this you can see that the value is pi over 4. There's also a similar formula when d is positive, so you have a real quadratic field. There L1 chi is equal to 2 times log of eta, which is some fundamental unit, times the class number divided by square root. So this is and okay, for details, you can go check those notes. Another reference for this is just the Wikipedia article on the class number formula. And there, I think they actually give something a little bit yeah, they give some more something a little bit more explicit. They say okay, so you can go and check that out. There are formulas for these things, and the reason why this class number formula pops up is kind of interesting. So why do class numbers, etc., why is there anything about imaginary quadratic fields coming up? And the reason is because if you look at Q adjoin square root of minus 1, then the ring of integers, so okay, these are called the Gaussian integers. And there's a norm, and the norm of a plus b times the square root of minus 1 is equal to a squared plus b squared. So it's telling you sum of two squares, right? So we're really asking about how many ways an integer, or how many um, ideals in the ring of integers, or elements in the ring of integers, are um, give you a norm of n in the Gaussian integers. And there's this thing called the Dedekind zeta function, which counts these things. So the Dedekind zeta function is the sum. Let me. So it's the sum of the ideals in the ring of integers, and then it's 1 over the norm of the ideal to the sth power. And so this is denoted zeta sub k of s, and it's equal to this. And you can see that this is counting the thing that we want to count, right? So it's, again, the statistical question of we are producing a Dirichlet series and counting using the analytic properties of that Dirichlet series. The Dedekind zeta function has this property for quadratic fields K, that it is equal to zeta of s times L s chi. Well, maybe I won't write chi here. Maybe I'll just write this Kronecker symbol. I believe it's the discriminant and not d. Let me see if I can check real quick. Okay, I'm not totally sure if this is ls delta or n, or just d or n. So you can look this up. It's well known, but the point is that for quadratic fields K, this Dedekind zeta function factors as this product. So what we were looking at when we were looking at the number of ways you can represent n as a sum of two squares, well, here when we're looking at ideals, there's this plus minus 1 ambiguity, so we get that factor of 4, and other than that, this is sort of counting exactly what we want to count. And this factorization here, that's exactly what we observed here, right? That this Dirichlet series that's counting the number, essentially the number of elements, or the number of ideals in the ring of integers, the number of Gaussian integers that have a given norm n, we saw that factored as a product of the zeta function times this Dirichlet L function. I guess this means for sure that this is d and not delta. Okay. So from this perspective, what we're doing is we're really talking about this imaginary quadratic field that's sort of lurking under the surface for this question, and by thinking about it explicitly in terms of the arithmetic of number fields, instead of some sort of more ad hoc elementary manipulations that are used to that could otherwise be used to produce this, sort of things go quite smoothly, and we can use the class number formula to understand the distribution of representations, sums of squares. So what do we end up getting after all of this? Well, what we end up getting is that the sum n less than x of the number of ways to represent n as the sum of two squares is asymptotically pi times x, right? And so this pi is coming from this pi over 4 right here, and then you have this 4. So asymptotically, so on average, there are pi ways to write n as a sum of two squares. And that's pretty cool, right? You know, I don't know, maybe you wouldn't have expected pi to just show up like this. It's kind of nifty. Getting a good error term here is tricky. I think the best might be square root x or square root x plus epsilon, but that's something that maybe you can look into using the references that I mentioned previously.